Hello, everyone. Great to have you here. As always, good to see some familiar names and faces in the chat. If you're new, of course, you're just as welcome, so I'm glad you made it, but good to see everybody. We had a week off, I guess, from our normal streams, although we had a great bonus session on Saturday in our Discord for the first homework assignment, so that was cool. If you happen to have a chance to join us for that, thank you for coming. It was a fun session, and maybe we should do these sorts of things again. So yeah, happy whatever holiday it happens to be where you are. It seems like that's a common refrain. Also, happy Olympics. I guess those are going on. No spoilers for me, please, because I'm gonna wait up and watch everything recorded after this is over with. But what's our favorite Olympic event, by the way? Nice to see curling. I like that there was a big argument about curling. I didn't watch the full thing, but I saw that there was an altercation on the curling rink, which is always funny to see. Good to see all the folks who say ice dancing and figure skating, because that's my favorite too. I don't know what it is about it that's so captivating, but that's definitely my favorite. And I guess that's going on. It's probably already happened, but I'm gonna get to watch the recording of it after this. So it's always an exciting evening for me. Been a good week. I made it very, very briefly to Tampa, so that was a big occasion for me, as you know, if you've been following these streams. And I posted the photo of that big achievement in our Discord. So that's also just a plug for our Discord, because it's a great environment. It's great for coming over there and having an open questions forum. We also, as I said, we had that bonus session on Saturday with working through some practice problems. It's a great place to just have it over there. And we also just have some random chat and community building. So it's an important part of what we do, that, you can have the opportunity to interact with each other and answer questions about your code and all these sorts of things, and just kind of enjoy everything. So we're about to get started. Reminders, we've got a soft deadline for the second set of practice exercises that's coming up. And thank you to those of you who submitted the questionnaire that we sent out, the survey. That told us that one of the things we probably should put together in some form or fashion is a project. So look out for more information about that soon. I think for now, you've got plenty to work on. We have 4 chapters worth of material that you can be completing and work on our practice problems for that. But I know if you're interested in taking the next steps, having access to a project is going to be something really helpful for that. So keep an eye out for how we set that up, because we recognize that it's something that people would like to see. So cool. We're going to find a way to do it. And for now, though, we're about to get started on our final chapter of this first part of Programming for Lovers. So it's my favorite chapter, I would say, of the 4 that we cover, for a couple reasons. It makes me happy. Number one, because we cover cellular automata. So I love the field of cellular automata. It's really neat. You may have seen cellular automata before. A lot of times I have worked with students who have seen the game of life before. And we cover cellular automata in a little bit of a different way. And we actually look at what the very first notion of what cellular automata were invented to study, which is this notion of self-replication. And it turns out that the application that we're going to see it produces a visual from very simple rules that's so pretty. And you can go and check our reading out on our Programming for Lovers website. But it's so pretty that it actually essentially launched an entire field called artificial life, which is not a field that people really necessarily these days have a lot of awareness of, because this was like 40 years ago. And it was sort of a version or an offshoot of what artificial intelligence was at that time. obviously things have changed quite a bit in the last 40 years, and what we think of as artificial intelligence these days is something very different. But it's essentially a visual that's so pretty that it launched an entire field. And then the other thing I love about this chapter is it's my favorite set of practice exercises from this first part of the course. So as what we'll see is, as we go through and enter into part 2, the type of applications that we can consider, the type of questions that we can look at are much more complex and advanced. And with that comes things that are more fun because we have greater power in order to build things out. So the practice problems here are something that's very close to what we're going to do with cellular automata, except it's going to seem very different. So we're going to be looking at systems of particles that can react and diffuse with each other in their environment. It turns out that even a simple model of this, like a predator-prey model, is going to produce some beautiful and very surprising patterns that answer at what it was at one point in time an open biological question. So that's a favorite homework assignment for me today. But at the moment, though, we're going to sort of build up to that. So we get a chance to step back and slow down a little bit and look at some of the basics that are going to prepare us for the work that we're going to do in this chapter over the next couple of weeks. I know I've had a couple questions from folks. If you're, one of the things I've said before is keep going on our treadmill. Like, do everything you can to just sort of stay on. And that doesn't mean you have to show up to every stream, although I'm happy to see everybody live and have you here. But by all means, try to stay with us as much as you can. We're going to have a break soon, so we'll take a break after part 1 of the course, and that'll allow us to sort of breathe and catch up and everything. So we're near the end, and keep going. I know you can do it, and today is an opportunity for us to kind of step back a little bit in the same way that we step back a little bit at the start of every chapter. Like, how do we work with strings? How do we generate random numbers? All that sort of stuff. So yeah, BZ, don't fall off, but we're here to help. That's why we have things like Discord too, so you're always welcome to join us there. But we're ready to start. One more thing I guess I would say before we begin. In the meantime, make sure to please like and subscribe our videos. If you're watching this, you might not think it's a big thing, but just clicking the like and subscribe button helps us become a little bit more visible, both to YouTube, of course, as well as it allows me to sort of do some work on my side, which is trying to bring other faculty to a project like this and demonstrating to my institution that, we have a great audience of folks who are out there and really engaging very positively in the material. So something as simple as liking and subscribing goes a long way with these sorts of things. So if you have a chance, make sure to do that if you haven't already. And of course, you can join Philomath for more support, and we'll be talking about additional features soon, including our project. But for now, we're ready to get started. So let's code. All right. So to get started, you're going to notice that I have some initial starter code here for us for working with two-dimensional arrays. And what I've done is I've created a folder called 2D arrays. And then within that, that's in my Python source code directory. And then I've got a main.py file. And when we start, I'm going to have the opportunity to ask you a question to think about, which is, when we say arrays, in Python, we're really talking about two different things. So we're thinking about tuples, and we're thinking about lists. And we've seen both of these ideas at the level of one-dimensional tuples and lists, meaning we have a collection of data that are represented in like one row. So we have, for example, when we were storing all of the Fibonacci numbers up to a given number n, you thought of these as just a collection of ordered variables going from the first thing to like the nth thing. And in this particular case, we're going to generalize that to a two-dimensional grid. But we're still going to have these two built-in things that Python provides to represent how we think of an array. We're going to have tuples and lists. And my warm-up question is, what is the difference between tuples and lists? I'll give you a hint that this is a review question from something that we've already had a chance to take a look at when we looked at these data structures on a one-dimensional level. So how is it that we remember the difference between tuples and lists. Good. A lot of good answers. Everybody remembers the important thing here, which is that tuples are immutable, but lists are mutable. And the short way of saying that is that with tuples, you can change individual elements. Or excuse me, with lists you can because they're mutable. And with tuples, you're not allowed to change individual elements of your array. This is going to apply in the two-dimensional case as well. So let me start with tuples. As was the case with lists in the one-dimensional case, most of the time we're probably going to use a list. Mutability is kind of a nice feature, but sometimes we have a collection of things that we want to store together, and we know we're not going to change that. And one example would be on the practice exercises accompanying this chapter. We already have a 3x3 matrix that we're going to need to work with. And before, I might declare a tuple by saying whatever the name of the tuple is and then equals and then parentheses. When I have a two-dimensional tuple, a nice way of writing this is to hit enter and think about this as sort of the outer parentheses. And we're thinking about a tuple as a collection. If it's two-dimensional tuple, it's a collection of one-dimensional tuples. And each of those one-dimensional tuples is going to correspond to a single row. So the first row that I'm going to create is going to be 0.5. So this is going to be a 3x3 tuple of floats. And they're going to have the specific values 0.05, 0.2, and 0.05. And then at the end of this row, I'll have a comma. The second row, which also is going to go into parentheses, is going to be 0.20, 0.00, 0.20. And then the final row is the same as the initial row. So I could copy it down, or I could just retype 0.05, 0.20, 0.05. It might not be clear at all yet what is special about this 3x3 tuple. That's fine. When you do the practice exercises, you'll see that this is going to help us represent a diffusion process, but more on that later when you do the practice exercises. For now, it makes sense for me to print this thing. So I'm just going to call print of my tuple, and I want to run my code. And to do that, I'm going to make sure that I'm in the src directory. And once I'm there, I can navigate to my 2D arrays directory within it. And then I can call Python3 or Python if I'm on a Windows machine, and then main.py to run the code that's in main.py after I've saved it. And so the kernel gets printed, and it's not attractive. We'll talk later. So we're going to print some tuples and lists, and one of the things that you'll see is the default printing is not necessarily going to be the prettiest. And so we'll take an opportunity at the end of the code along to come back and talk about how it is that we might print this in a nicer fashion. But what we can see is we think of this two-dimensional tuple as a tuple of length 3, where each element is itself a tuple of length 3. So that way of thinking about tuples and lists in general is going to be productive. And it will also allow us to think about how we create these things in general and how we access them. So I could, of course, let's say we can access individual elements too. So I could print, for example, kernel of 0, 2. And so I access the element in row 0, column 2. Everything is 0 indexed, using the notation kernel of 0, 2 with brackets in this way. And I could print another couple values, and then I'll point out where they are. So let's do kernel of 1, 1. And then we can also do kernel of 2, 1. And so kernel of 0, 2 means the element that's in row 0 and then column 2. So we look at the row, or the tuple, that is at position 0 of the kernel. So that's this row. and then we look at the element that's in position or index 2 within that row. So we're printing out this value. 1, 1 is going to be printing out the element in the middle since that's in row 1, and then it's at column index 1 within it. So it's going to print 0.00. And then 2, 1 corresponds to row 2, and then this is element 0, this is element index 1. So we should see 0.05, 0, and 0.2 printed. When I save this, I hit up in the terminal, and then I run, and we'll see those 3 elements get printed. So far, so good. Because you were very smart, you told me that we know that tuples are immutable. That means that I cannot change individual elements. So if you tried to do something like setting kernel of 1, 0 equal to 0.7, and you ran this, well, of course, you'd get this type error that tells us that a tuple object does not support item assignment. So we're not able to assign individual elements. Nevertheless, kernels are useful if you know exactly how big they need to be in advance. This indexing will work for lists as well. So when if we declare a list, then instead of using parentheses, we're going to use brackets if it's a fixed size. But the indexing of the lists is going to proceed in the same way, as you might guess, since the indexing in the one-dimensional case was the same for tuples and lists. Let's see then how to declare a two-dimensional list. So I want you to imagine, and we've got our simple figure from the text, of a matrix that has 7 rows that are indexed 0 through 6, and then 4 columns that are indexed 0 through 3. So this element, for example, would be at row 1, column 2. And if we were to declare something like that, I want you to think about how you might imagine if I were to declare this list that is 7 rows by 4 columns. How do you think we might do this? Here's an opportunity for a question to the chat. And I should say, let's have default 0 values. Let me give you a little bit more. The chat has some creative ideas. I like them. One way would be to manually go through and make 7 separate empty lists, which is a reasonable idea, and then we could set the values. Now, that will work, of course, when I make this 70 rows by 40 columns. You probably don't want to type out all that much, but fair enough. And some other good thoughts. So one of the things we could do would be to do some sort of ranging. That would be nice. So we need to range over 7 things, and for each of the 7 things we need to create something. That's a great idea if you have that. And then a couple folks say, well, we know how to declare one row with 4 elements in it. So if I want to have one row with 4 elements in it, I would have just said A equals 0 times 4. That's a nice built-in way that Python provides, right? For setting a bunch of default values equal to 0. And then, well, if I have 7 rows, then what I really want is 7 copies of this thing. So if this is what I want, and then I want 7 of them, I could take brackets around that, and then I can multiply by 7. From my perspective, based off of what we have done, that is the most intuitive way of creating your list that has 7 rows and 4 columns. And now we can set a value. So this will work. It's going to, I suppose I could print it to show you that everything is going to be okay. So we see, as we would hope, that we see 1, 2, 3, 4, 5, 6, 7 rows, each containing 4 elements. And the other thing I probably should do is to set a value. So I'm going to set, like in our 2D array, I said this was a of 1, 2. Let's set it to be equal to something. So let's set a of 1, 2 is equal to 19. And then I'm going to print out my 2-dimensional list. And my question, of course, is, well, what do you think gets printed? Here's an opportunity for me to test what you think. John says, what I think probably should happen is, well, we should change the element at position 1, 2. This can't be a trick question, can it? So we know that that's the second row, or the row at index 1, and then the element within it at index 2. So we should see this value here when we print it again. That should change to a 19. I think that's reasonable. So let's see what happens when I run the code again. And what we actually see is something very different, which is the value 19 in that element at position 2, or index 2, in all of the rows, not just the one that we wanted to set. So we're setting every single element at index 2 of any row equal to 19. Now, my one question was, what I would say here is, first off, BZ said that they were struggling with the treadmill and they didn't know if they could make it, but they were going to do their best. And then they immediately came out with this great answer of knowing exactly what was going to happen. So I think you're pretty well on the treadmill. I'm not worried about you too much there. First things first. My real question here for you is, does this seem confusing? Or does this seem natural? There's two good answers. One, okay, fair. We don't know object-oriented programming yet. That's a fantastic plug for literally our next topic, where we're going to investigate object-oriented programming, and we'll understand this a little bit. There's another answer which everybody else has, though, I think, which is it does seem confusing, and it does seem pretty unnatural. And the reason why is that this is horrendous Python stuff. It's okay, we're going to be able to get around it, but this is an example of the type of thing that, I mean, could there be anything more natural to do that anyone could possibly come to a language and want to do, to say, well, I know how to create a list of length 4. It's this, and I just want 7 copies of that, and now I get to set my value, and the next thing you know, you set every value in the entire 2-dimensional list. Like, in what universe does this possibly make any sense? And sure, is there an explanation for this? Of course there's an explanation for it, and you're going to appreciate that later. But in the meantime, this just seems to me like senseless frustration, because we've got to take the way that we learned how to do something, which was totally reasonable in the one-dimensional case, and now all of a sudden it's not going to work in the two-dimensional case. What are we doing? This is another subtle point too, which is that we haven't really talked about memory management. We need to talk about object-oriented programming. We need to talk about memory management. Both of those things are going to help resolve circumstances like this that we see. And a lot of those topics, when you study programming in other languages, they might seem challenging if you have to address them at first. But then once you've learned a little bit about it, you have this appreciation for what's actually going on, and you're empowered to understand what's happening underneath everything. Python kind of tries to hide this from you, especially if you're coming to programming for the first time. And the unfortunate thing about it is that then you can walk into a trap that you don't even really understand, only because there is a complex explanation for this. But what actually has happened is that Python didn't make 7 lists. It makes 1 list, and then it makes 7 references to that 1 list. So in this way, if you change the element at position 2 of any of those lists, they're all going to update, which is not even necessarily a bad feature if that's what you wanted, but that doesn't really seem like it's what we would want when we're just declaring a list. So there's nothing special about row 1. I can rerun this and I'm going to get the same behavior regardless of which row index I give it, but it just seems a little bizarre at best for us to have this happen. Let's see the better way then. Okay, my Python rant's over for today. That's probably the only real one. Well, there's going to be a little bit of a minor one, but for now, let's see how we fix this. So we're going to say we can fix this by instead, so I guess I'll comment this out. And I'll save that a of 1, 2 is equal to 19. But in the meantime, I could say, let's make an empty list. And I'm going to fix it in a couple ways, but I'm going to make an empty list, and then somebody had a great comment in the chat, why don't I just range over the things that I want and then make each individual row? So if I want a matrix that has 7 rows in it, I can create each of those rows individually. So I could have a range that doesn't use the row index here, but just ranges from 0 to up to, but not including 7. At each stage, it makes the row that we care about. And then at the end of this process, we append that new row that I made to A. And that might not seem like it's any different from what we were doing before, but creating the data in this way by saying at each stage, each time through the loop, I'm creating a new row that has 4 default 0 values in it, and I'm appending each of those to new row. That's going to make all the difference in the world. So when we run it this time, and I'm going to set a of 1, 2 equal to 19. I'm also going to, let's set a couple of other things. We're going to set a of 0, 0. This is the top left element. So if we look at our 2D array, we're setting this element here. And the other one I'm going to set is 6, 3, so that we can practice with setting, say, the bottom right element. So it probably isn't surprising that if there are 7 rows, they're going to range from 0 to 6 in terms of their indices, and each row has 4 elements which will range between 0 and 3. So we can set a of 6, 3 equal to something that we like, 100 for example. So now when we save this, and let me set this one equal to 42. When we save this and then we run it, you'll see the top left element is here. It got set to 42. Our element from before got set to 19. This is at row 1, column 2. And then the bottom right element, which is in row 6, column 3, got set to 100. So everything appears to be right with the world. All right. Now here is the time at which, and I'm surprised it hasn't happened in the chat already, but here is the time, the point at which all the Python people who are like very much, all the Pythonistas will get really angry at me, and they'll say, but there's such a more natural way of creating our list, and I'll show you why. So this is a little bit clunky. I love this. And there's certain languages where something like this or similar to this would be a very standard way of making something, which is I need a two-dimensional list. Well, let's make a bunch of one-dimensional lists, and then we're just going to add them on to our growing list. There's a one-line way of doing it, though, that I'm going to show you. And I say we could also declare our list using a comprehension. And the comprehension would say, I'm going to comment this out just so that I don't have the same declaration of A twice. But I would say A is equal to, I'm still going to do 0 times 4. So this is okay, but I'm going to do it a bunch of times. So I'm going to add the for loop within the declaration of the list. So I'm going to say for underscore in range of 7. And then I'm going to close the bracket. And this notation, which looks so similar to what Python got mad at us about, is actually going to be okay. So I'll show you by saving this and running it. And you'll see I've kind of updated A to be the same thing. And you'll see the same values got set. So we didn't incur the issue that we had before, and now we have what's called a list comprehension. This is the type of Python feature that just gives me the absolute heebie-jeebies. This is not a Python rant. I understand why this type of thing exists, and I kind of appreciate it. I just think it's ugly at best. And sometimes, like if you look at enough of these, then you kind of brainwash yourself into thinking, into like seeing this as natural. But just in terms of programming in other languages, I don't mind that I need 4 lines to say I'm making an empty list, I'm ranging over the rows, I'm going to make a row, and I'm going to append it. That just, to me, just feels so natural and comfortable. And yeah, I had to type a little bit more. I'm probably going to pay for it with arthritis or something in 30 years, but it's worth it. This is not the most readable, but sometimes you can kind of, for a simple task like this, if you get comfortable with it, I'd say, yeah, it's 0 times 4. And I do this for a bunch of copies. So yeah, I get 7 copies of it. Oh, it's a 7x4 array. But it's also just sort of, it's a tough one for me to, I appreciate it, but it's a tough one for me in a course that involves people who haven't programmed that much before or aren't comfortable programming. You type something like this out and the energy in the room just dies because somebody who hasn't programmed before says, I don't know if I like that. Like, I might just hop off the treadmill. And all I have to say to that is, if you understand this, you don't ever have to declare a 2-dimensional array with a list comprehension. You can do it this way. I won't mind. I'll like you even more. So Python is, kind of helpful in some ways. In some ways, it has these really nice things, and I always try to make sure I give Python a compliment. I don't want the Pythonistas chasing me down and yelling at me. But there are times where it just, for beginners, I don't think this is the most natural. But I will say, sometimes I'll use one versus the other. I might use these interchangeably. I think that also doesn't do beginners the greatest service, because then it's just easier to get comfortable working with one way of doing things instead of 2. And that's a classic Python thing, right? Like, let's give you 30 ways of doing things, and then you're going to have to know all 30 of them and somehow apply the one that seems like it's the most appropriate in each case. That's not sort of what I like the most about languages. I like just having one good way, but we'll use this sometimes. Probably a lot of the times we'll do it this way. But if you're curious, can we use a list comprehension? Yeah, a lot of the times the answer is yes. Now, we can access individual elements of our list. We also can access, say, other interesting things that we would want to access about a 2-dimensional list. For example, how many rows and columns does this thing have? And so I'll say we can get the number of rows and columns. I'll print the number of rows is equal to len of A. So that might not be surprising, since how we're thinking about a two-dimensional list is as a list of lists, in the sense that there are 7 things. Each one of them is a list of length 4. So all of our 7 things have 4 elements in them. And so the number of things in the overall list is 7. Then in terms of the number of columns, well, the number of columns is just the number of elements in any row. So the number of columns is, and you always want to be careful accessing A of 0, because you want to make sure A of 0 actually exists. But the row at index I is just A of I. And so if we're interested in knowing the number of columns of this thing, well, it's just the number of elements in that initial row. One critical point, of course, is that just because you have a two-dimensional list doesn't necessarily mean that it's rectangular. So we can have non-rectangular lists too. So for example, and here's an example of something that is just way easier for me to declare in this notation. I think, I mean, you can use a comprehension as well, but I want you to imagine that we want to make like a triangle, like a right triangle of lists, where the first list is going to be empty, the second one's going to have 1 element, then the next one's going to have 2, the next one's going to have 3. So if I have just a little triangle of lists, and I'm going to call this numRows is going to be equal to 4. I'm going to call this board, and I'm going to make it an empty list initially. And then I'm going to range over the number of rows. So I'm going to do 0, 1, 2, 3. And then I'm going to append to board a collection of false values. We're getting in the mindset to work with game of life boards where everything is either going to be true or false. And a lot of times we'll just initialize everything to false. So this is going to be a triangular board, and I'm going to set, say, for the current row index, I'm going to give it row number of falses. So I'm going to change that from underscore to row. And then at the end of this process, well, let's print board. And I will move my print A statement up a little bit so it won't interfere with what we're doing here. So we can run this, and when we print the board, you'll see we have an empty list at the start, then 1 false element, then 2 false elements, and then 3 false elements. And so if you had tried to access something in this row, or you access the length of this row, it would have given you 0. That's not really representing the number of columns in this, because the number of columns in this doesn't really make a lot of sense. Each row has a different number of elements in it, and so as a result, it's non-rectangular. I introduced this board so we can get a little bit of practice just seeing, how is it that we might append to a two-dimensional list. Appending is something that's so natural to want to be able to do. And so let's add a false to every row of the board. And what we could do is to say, well, we could range over the number of rows. And so I could access that with numRows, or I guess I could also access it with length of board. They're going to give me the same end result. And then for this individual row, I want to append a false value to it. So I know how to access the current row of board. That's with board of row, which is what we had said. And then we can append to that false. So I'll save the print statement for after we do this. And what you'll see is an additional false value, hopefully, at the end of all of these rows of my board. So when I save it and then I run, we now have something that's got 1 value in the first row, then 2, then 3, then 4. So this is just getting comfortable working with lists and extending everything that we have done in the one-dimensional case into the two-dimensional case. So we've seen a little about tuples, we've seen a little about lists in general, we've seen how to access individual elements and change them, and we've now seen how to access something like the row at index I of the list, as well as being able to append entire rows. So this appends an entire row to the board, and this append is appending a single value to a given row that we have. Okay. Alistair says, what happens to the empty value at board of 0, 0? There actually wasn't anything there. So if you had tried to access board of 0, 0 before, I think you would have been in for a painful surprise. So if I saved that before I added that, you're going to get a list index out of range because board of 0 exists, but board of 0, 0 doesn't. So board of 0 is just an empty list at this stage in time. And so you can print that printed here, and you get an empty list. But there's nothing at board 0, 0. So this is what creates it at board 0, 0 when we append to it. Like down here, print board 0, 0, everything's going to be okay because we added that false value. Good question. All right. Now, what we want to do is use all this now that we're comfortable with it. That's our rapid introduction to tuples and lists in 2 dimensions. And we're actually going to need multi-dimensional lists as well, but the step from 2-dimensional lists to multiple dimensional lists is very tiny compared to the step from 1-dimensional lists to 2-dimensional lists. You can imagine, for example, if I want a cube, a grid of cubes, well, okay, this aside, you just need to nest another for loop, and then you could create 2-dimensional lists and append all those to your growing list A, and all that would do would be a little bit more confusing, but it wouldn't ultimately change what it is that we're learning about. And of course, you'd want to avoid statements like this. But for now, I think it makes sense for us to say, well, if we're working with lists, what does that really mean? And the natural way of what I mean by that is involving 2-dimensional lists and functions. So we might imagine that we want to write a function involving a list, and I'm going to write a function that is relatively straightforward. So I'll come up with the simplest function I can write, which is just going to set the first element to true of a given list, 2-dimensional list of Booleans. And it's not going to return anything. Not going to return anything. And I'm going to have a very, I don't want that long doc string, but I'm going to have a very short doc string that just says sets the element in the top left of a given 2-dimensional Boolean list to true. And so all it needs to do is to set a of 0, 0 is equal to true. We should be careful about something like that because we need to make sure that this element actually exists. So of course we probably need to raise a value error if we have length of A is equal to 0. Or if it's the case that, well, A of 0 exists, but it's empty, like what we had before when we first created our board containing false values, that initial row didn't have anything in it. So if it's the case that length of A0 is equal to 0, we could raise a value error and say error invalid dimensions of board. Okay. And if you're thinking in the way that I've tried to brainwash you to think, there's also one other thing that's missing, which is this is the old school Python way of writing things where I don't have to worry about thinking about what A is. But I know what A is. A is a 2-dimensional Boolean list. And so what we're going to do is specify that, but I didn't want to confuse you by writing that out initially. So we're going to have a type int for A, and A is going to be a 1-dimensional list of bools would be list of bools. A 2-dimensional list of bools is going to be, well, it's a list where every element is a list of bools. So I want you to think about it almost as if there's parentheses here, right? It's a list. And what are the elements of that list? Well, each element of the list is its own list. So that's how I want you to always think about two-dimensional lists, which is this whole thing is a list. Each element is one of the rows. Okay, so that's one of the elements of the list, another element of the list, and so forth. You say, what are the elements of the list? Each one is its own list. So A is a list where each subsequent element is a row corresponding to a list of Booleans. So that's our notation for the type int. That's what the type of this thing is. And we're going to see when we work with cellular automata, I can actually, even though I know that this is a two-dimensional list of bools, I probably will want to think about this as a game board instead of as a two-dimensional list of bools. I want to keep both of those thoughts in my mind. And so Python is going to give us, as many languages do, it's going to give us an abstraction that's going to move us towards object-oriented thinking that will allow us to think of this as a two-dimensional list of Booleans, but also just call it something else, like a game board. But hold on to that thought for now. We're going to see it later. My question for now is I want to go in, and after I've called print board, I want to set first element to true of board, and then I want to print it again. And my question for you is, what is going to get printed? In particular, you might think, well, I'm printing board of 0, 0. That's really what I'm interested in. This isn't a trick in the same way that when we declared two-dimensional lists, I was tricking you a little bit by saying, well, a bunch of values changed. The only value I'm really interested in is board of 0, 0, which for our board is just this guy. So does it become a true or does it become a false, and why? And the answer is, well, one of the things we know about lists is that they're mutable. The other thing that we know is, and this differentiates them from tuples and strings and these sorts of things, is that lists in the one-dimensional case are passed by reference. So if I were to print board or board of 0, 0, and I'm interested in seeing what that value is, I could print the whole board, it doesn't matter. There's only two possibilities. It could stay false or it could go to true. And that value is going to go to true. And the reason why is because when you pass a two-dimensional list into a function, just as in the one-dimensional case, it is passed by reference, which means you are able to set the values of the board that you passed in as the reference to the function. One more main thing I want to do in this code along is to look at this idea of printing. So I don't know about you, I'm tired of printing boards in this way. They're coming out pretty ugly. So we should probably once and for all fix this. And one of the things I'll do is write a function to do that. So let's write a function called print board. And here's actually an example of where you might not specify a type hint. I guess you could print values that aren't dependent on the type that it is. Although that could get us into trouble with what I want to do. So I'm still going to keep this as a two-dimensional list of bools, a list of bools. And it's not going to return anything. And I could say, well, what is this thing going to do? All it does is prints a 2D list of Boolean values in a pretty fashion. Okay, so as you might imagine, where each individual element is going to get assigned, within a row, it's going to get spaced out and printed, and then every new row is going to be on a new line. This is not what we're getting here, where everything's kind of getting printed out on one line. That's okay, we just need a little function to do it. And there's a natural way of writing a function like this. I think there's the standard introductory programming way of writing this function, which is to say, okay, I could do some error checking, but I'll assume that we actually have some values. And either way, I'm going to range over length of the board. And I want the current row index is going to be equal to R. And then once I'm in a given row, I want to range over the current row, which is board of R. And the length of that current row is just going to tell me how many elements are in it. So this is, I think, probably just a recall from when we worked with one-dimensional lists. So we've seen this quite a bit. You range over a one-dimensional list in this way. And so you range over the rows of a two-dimensional list in this way as well. And then once you're ranging over those rows, well, the current row is board of R. Its length is the number of columns, I suppose, or the number of elements in the current row. And C is going to range all over those. So the current element then is just board of RC. And if I want to print that, one of the things I could do would be to print board of RC. Although that will cause a problem, which is what? Can somebody tell me what is the issue that's going to arise if I write print board of RC, and then in main, for example, I'm going to call print board of board. Good, good. You're all with me. I love it. So we know when we call print, print produces what is given to it, and then it gives us a new line, which is a good thing. So this is not exactly what we might have expected when it came to printing the board. So we don't want to print each element on its own line, of course. We want to print each row on its own line. And to get at this, I'm going to do something that we haven't actually needed in terms of printing in Python yet, but that's very important and that I should probably show you. So there's something new here, which is if you don't want a new line, you can specify a second parameter indicating what you want to print after each element. And after each element, I just want to print a space. So we say end equals, and then I give it one space within double quotes as a string. If you don't add this, then there is a hidden default parameter, which is to not do this, which is to add a new line. This keyboard is so well worn that the N and the M have both all been rubbed off, so sometimes I type an N instead of an M or vice versa. Anyway, this is the default behavior that you have when you print board of RC just on its own. So you're adding this new line symbol. What we want to do is instead add a space. Now, my next question is, when I run this, so if I save this, I come down here, hit up in the terminal, run it again, what am I going to see this time? What will I see this time? There's John, good. Yeah, in this case, when I print it, I lost carriage returns entirely. So I've kind of gone back to the original thing, where now I'm printing all the values and they all just get printed consecutively. So fortunately, there's a reasonably easy way of fixing this. We just need to say, well, at the end of every row, which is going to be here, so it's after I've ranged over all of these elements in the row, I'm at the end of the row. And we should print a new line. That's such a simple task that it might actually even seem hard, but we can print a new line just by calling print and then just not giving it anything. So if you don't give it anything, then you're going to get that end is equal to the new line as the default. Or you could, a little bit fancier is just to print an empty string, although if you don't give it an input, it's the same difference. So whichever of these that you prefer, doesn't matter. When we now save this and we run it, we're going to get what we wanted, which is now we see our little pyramid of true, false, 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 false. And that's been printed in this pretty fashion. Even this, though, can be improved. My question is, how can we make this better? Even though this is the standard way, if you're writing a print board function, probably most programming courses come at this. I think there is a much better way of doing it. My question for you is, what is that way? How do I do this better? My hint is you'll remember there's something that I don't like. List comprehension is just intentionally trying to trigger me. I forgive you, but sure, we could probably use a list comprehension. I'm not going to go that route, but what do I not like? Oh, I guess you were saying maybe I don't like list comprehensions. Okay. But I don't, there's something about our current code that I'm not a huge fan of. And I think often is something that other people will say, yeah, that a lot of times there's no need for them. All right, Remy, thank you. You saved this. So I don't like nested loops. That's right, I don't like nested loops. And a lot of people don't. I think they're perfectly reasonable in some circumstances. In this particular case, you can get very comfortable with this. And we'll even sometimes in the course, I might do something like this. But I think there's still nevertheless a way of writing this in a way that I think makes things look just a little bit prettier and more natural, instead of thinking, well, I'm ranging over the rows and then I got to range over all the columns and I got to make sure I remember to put a new line at the end of this. I think all of this can kind of just get solved by ignoring this completely. I'm probably going to wind up retyping it, but ignoring all this completely and just saying, all I want to do is range over the elements of the board. And what are the elements of board? Board is a two-dimensional list. Okay, we need to think it's a two-dimensional list, but it's a list of a bunch of other lists. So if it's just a list, each element is a list. And so if I range over the board by just saying for row in board, I'll just tell you, row is a one-dimensional list of bools. And unlike list comprehensions, this kind of thing to me just looks very natural. Oh, what is a board? It's a two-dimensional list. It's a list of lists. What does an element mean? It's a one-dimensional list. And then what do I want to do with that row? I want to print it. And my function can just look like that. Of course, I haven't written my print row subroutine, so I probably should write my print row subroutine. And then I think, well, what does it take as an input? It's taking a single row, which is just a one-dimensional list of Booleans. And it's still not going to return anything. And I'm going to be really bad and not write a docstring for this because I don't think I really need to think through that here. But if I'm given a one-dimensional list of Booleans, I'm going to say, well, how would I print that? And I would say the same thing applies. If I gave you a one-dimensional list of Booleans, you'd say, what are the values in that list? And then I would print the value. And so I'll just call another function called print_cell_eval. Now I could just print it. You might wonder why not just print it with the end equal to the gap. Because I'm going to do something a little fancier here, just for fun when we finish. And then at the end of this, I need to print. So I still need a new line at the end of the row, of course. But to me now, this looks so much easier. Like it makes sense as to why it's here. And whereas before, if you've programmed before, it probably looked perfectly reasonable. But I'm print a board by ranging over the rows and printing the rows. And then I print a row by ranging over the cells and printing the values. And then making sure I print a new line at the end. So the only thing that remains is we've somehow gone mad with subroutines, but let's write a simple print cell function that takes a Boolean as input and doesn't return anything, but then we can give it different things to print. So what I was going to do is to say if value, and by that I mean if value is true, then we want to print one thing, and we could print like an X or something. I guess that might, let's print an O. And then we need to say end equal our space symbol. Otherwise, we're going to print, say, an X, and our end is equal to space. And as before, this is going to prevent the new line from happening. So we want to make sure that we do it that way. And now we could call printboard again, and I could save it and run it. And when we print it, now we've simplified the values that we see, and we see 0 as a true and X as a false. I'm going to do something a little bit better or a little bit prettier than that. And what I want to do is, why don't we make this, we're going to kind of head towards finishing up with the basics of two-dimensional tuples and lists. And I want to point us towards what we want to do next, which is to implement the game of life, be able to draw the game of life, animate it, be able to draw an arbitrary cellular automaton and see how it changes over time. We want to do all of those things. We have all of the foundation. We'll need to look at drawing next. But in terms of implementing the game of life, we could go off and do it now. We're not going to, because it's going to consume its own code along. But we have what we need, which is nice. We can build something pretty beautiful with what we've learned thus now. But I want to prepare us for that first by saying, well, here's one of the most, if not the most famous initial configurations of a cellular automaton, which is this R pentomino in the game of life. And the dark cells here correspond to things that are alive, and the lighter cells correspond to dead cells. I'm going to use true to represent the alive cells and false to represent the dead cells. And let's visualize this thing before we stop. So what I would like to do is to say, let's go to main, and let's create, so I'm going to say, we know that this is a 5x5 board, so let's create the R pentomino by saying the number of rows is equal to 5, and the number of rows is equal to 5, and the number of calls is equal to 5 too. And then here I want to declare the R pentomino with everything starting to false. And we could do this in a couple of ways. We could use sort of the for-line approach where we do a for loop ranging. I think this is not too bad of an instance of declaring the R pentomino with a list comprehension. So I'm just going to go ahead and do it and make the Pythonistas happy with me. So we're going to make a list. It's going to be false times num calls, and then for underscore, which, because we don't care about the row index, in range of num rows. And then once we've done that, now we just set the values of the list. And I will leave this to you. So this is a good wrap-up exercise because it's a good practice for just getting comfortable with how we index two-dimensional arrays. So I'll remind you that this is what the R pentomino looks like. You need to be setting some of these cells to alive because currently everybody is dead in terms of the R pentomino that we declared. So we have a 5x5 collection of cells, but they're all set to false. So which values do we need to set in order to set the R pentomino? I'll let you take a look at that, and then we're going to discuss. So we know that our pentomino is 5 by 5. To set the values that we care about, we know that we're interested in values in rows 1, 2, and 3. And in row 1, we're looking at column 2 and 3. In row 2, we're looking at column 1 and 2. And in row 3, we're looking at element 2. So as a result, we can just take that idea, use what we've learned already, and set the values of the list. So to do that, we'll say, let's set some values. Our pentomino of 1, 2 is going to be set to true. And we're going to set all these other values to true as well. So our pentomino of 1 and 3 is going to be set to true. Those are the two values in row 1. And then the two values that we care about in row 2 are our pentomino of 2, 1 and our pentomino of 2, 2. And then we have the final element of the R pentomino. So when we look at it, we have 2, 1 and 2, 2. And now we have, this is row 3, column 2. So we also need to set our pentomino of 3, 2 equal to true. And now we can call print board. And so once I've set that, I can now print the board. And so we just give our pentomino as input to that, and we'll see the board gets printed when I hit up to rerun the code. Let's separate this out just a little bit. I'm going to say now printing the R pentomino so that you'll see the difference between these two things. So when I rerun it, you'll see, okay, there's our R pentomino. It looks pretty good. Has the right shape. I think I can make it a little prettier. So just in a short amount of time, I can make it prettier. Let's do, for example, when we print the cells. Let's give it our favorite emojis. So I wanted to find something that indicated kind of alive and dead. So for alive, I'm going to do heart eyes. And then for dead, well, what else could we do other than the skull? And so I changed just my print cell function. And I could change these to whatever I liked. And once I've changed that, I can save it. I can run it again. And now you'll see the live cells are going to get these heart eyes emojis, and then the skulls are going to represent the dead cells. So there is the R pentomino still represented in our 5 by 5 grid. And we can now represent any arbitrary automaton, although I don't think this is necessarily the direction that we want to go. The direction that we do want to go is, great, we can print this thing, right? But that's not what we really want to do. What we really would like to do is make an image of the board. Like, we have our R pentomino, let's make this. And we'll make a prettier version of this without doing a huge amount of work. We're going to need to investigate how to draw things in Python. But I kind of need to do 3 things. One, I need to draw one board. So all I've done is just print some representation of the board. And knowing how to do that's useful because I'm going to take everything that we have just learned and apply it to working with an existing package in Python for drawing things. And so this was all helpful, but I need to level up what I'm doing and make something like this. In fact, we're going to make something that's prettier than this. The other thing I want to do is, and I would suggest to do our reading and learn about the game of life if you haven't already, how can I animate this game of life over multiple generations so I can see this thing change and grow and form new live cells and so forth over time? That's not something that we're close to doing yet, and it's just a matter of being able to draw a bunch of static images. So once I can draw, it's going to be just like what we've seen elsewhere in the course. Once I can do things one time, I can do things n times. So if we're doing things n times, I'm just going to need a collection of boards. And now you're going to see why we need this transition towards multidimensional arrays, because, well, what's a board? It's a 2-dimensional list of Booleans. How would I represent a collection of many boards? Now I have a list of those boards, which means I have a list of 2-dimensional lists of Booleans, or a list of lists. So this is why, more than anything, we're going to need this very gentle translation towards object-oriented programming, where really what I want to think about is not necessarily that as a three-dimensional list, but as a list of game boards. So I'm going to have, this is going to be generation 0. I'm going to have another game board that's going to be generation 1 and generation 2 and so forth. And then what I need is some drawing code to draw each individual one of those boards, and then some helper code to combine all of those images into a big animation, which is a very standard thing to do in programming. The cool thing is we're going to be essentially ready to do that next time when we learn more about drawing in Python. And then we can do the really fun things, which are spending a lot of time digging into how is it that we implement the game of life so we can get this thing to come alive and change and grow over time. And then we can do even other things like build an engine that's going to work for an arbitrary collection of cellular automata and not just stop at the game of life. So that's why I find this section or this chapter so exciting. But we're going to need to spend another code along just on drawing things to help us make things pretty. And as for now, that's going to be it. So as I said before, please, as always, like and subscribe. Connect with us on all of our platforms. And I'll see you next time. But until I see you next, happy coding.